All right. So I think this is a fun thing to understand is, um, so here are various jobs that you have to do in the morning, right? You have to put on your underwear, you have to put on your pants and your shoes and your socks, right? And I use this example because when my son was little, he was horribly slow at getting dressed. And one day he says to me, Dad, I'm going to get dressed faster than you now because I have this new strategy in which I put on my socks first. And I didn't understand why that was going to get him dressed faster, but I love the fact that he got this sense of a total ordering, right? So we all know that you really should put on your underwear before you put on your pants, right? You should put on your pants before you put on your shoes, unless your pants are really baggy, right? You should put on your socks before your shoes, right? But it doesn't matter what he observed. It doesn't matter whether you put on your socks or your underwear first, right? So in a job setting, there's all these jobs that have to be done, and we put an edge, directed edge, if the one job has to be done before the other job, right? And then a very natural question is, give me a total ordering that respects these requirements, right? So one ordering is this, and this is probably your standard ordering, right? And you'll see for every edge, it's going forward on the ordering, right? And then my son comes along and he puts on his socks first, but every edge is still going forward, right? These are two different total orderings. And we say the total ordering respects this is called the partial ordering, right? Does that make sense? And what do you need in a partial ordering? You need it to be a DAG. What's a drag? It's a directed acyclic graph, right? Why can't you have cycles? Because if you have cycles, you don't know where to start, right? Everybody get the problem? Right? So cycles are a problem. All right. So again, I'm going to tell you the algorithm, and we're going to prove the algorithm works using an example. All right? So here's a DAG, right? There's no cycles. And what the algorithm is going to do is, well, it's going to first find a sink. What's a sink? It's a node that has no children. And then it's going to put, when it says, hey, let's put the sink last, right? And then it's going to delete that sink and repeat, right? So then it finds the sink, right? How long does it take to find, how do you find a sink? Well, you start anywhere and you just walk in the right direction, right? You just follow directed edges, and you know you won't cycle because there are no cycles, and you can't go forever because you're not cycling, and eventually you'll find a sink, right? But how long does that take? It could take you order n to find a sink, and you have to do it n times. You get n squared time, right? Nobody likes that. So what instead we're going to do is we're going to do depth first search. So you choose an arbitrary, right here. What's arbitrary? You know, if you talk to me, I'm talking, this is chosen by my adversary who wants my algorithm not to work, right? It's not a random one. It's a bad one. I start somewhere bad, right? And then I do depth first search, right? Like, everybody see that? And now I have a sink because we're done. So as F is popped off the stack, right? F is popped off the stack because there's nothing else there. We print it backwards, right? So F gets printed, then F's popped. And we're back at G, we go down to L, and then L's popped. And then we're at the G, and G's popped, and E's popped, and D's popped. Right, everybody buy that? And now our stack is empty, but the guys that we've printed, they have good solid breadcrumbs on them, right? So we're not going there again. So what do? We start at another arbitrary place, and we push on the stack, and as things come off, they get printed backwards, right? And then we start somewhere else arbitrary, and we do it again. Oh, this time we're at the root, which is nice because it will finish us off, right? Everybody good? And you say, why didn't we start at A? Well, if we knew that A was a sink, right? A sink has nothing coming in, then yeah, it would have been great to start at sinks, but maybe you don't know where the sinks are yet, right? This says it works even if you don't. If you start at the sink, it works, but it starts if you don't start at the sink. Yeah? Yeah, yeah, exactly, exactly, yeah. Sink is a node that doesn't have anybody coming in, oh, no, sink, no, sink's the bottom. What's the top? Source, sorry, he's right. These are, A is the source, F's the sink. Sounds like water, right? All right, good. Now we want to prove that this algorithm works, right? And what do I want to prove? I want to prove that every edge I want to prove that for every graph in any running of the algorithm, for every edge of the graph, the edge is respected, right? So if we're doing 1090, I say, give me an arbitrary graph. Give me an arbitrary running of the graph. Let's look at the output. Now give me an arbitrary edge. Let's see if that edge is respected, right? And so that's what I'm doing. I'm focused on one edge. All right? So there's the edge, and we want to see what happens. Does the edge get printed? We need to prove that U gets printed before V, right? So also, if you're taking 1090, we got cases. All right? First case. Do we know that U goes on first? No. We know that's a possibility. So it's a case. Here's the case where U goes on before V goes on, right? And then, well, there's this edge here. So we know that U's not coming off until V goes on. Right? Everybody agreed? In order to get U off, you have to handle all of U's edges. And this is an edge. So, and when you handle this edge, V's going on, right? So we know that V's going on next at some point before U comes off, right? And then V comes off and gets printed. Then U gets off, and gets printed. And, oh, look at, U got printed before, we got them in the right order, right? Everybody good with this case? It's the easy case, right? All right. So now let's look at another case. This is when V goes on first, all right? And now we're going to have subcases. The one subcase is V, right? We don't know that U is going to be found because it's a directed edge. Maybe U gets found before we take V off. Maybe it doesn't, right? So let's have two cases. One case is V comes off, and then U has to go on eventually, and then U comes off. And look at, it was in the right order, right? Everybody good? All right, so now we need a third case. V goes on, and U goes on before V comes off. Why are we saying this? It's a case, right? We're considering all the cases. Everybody good? Right, so this is the case. Now what's going to happen? U's going to come off, then V's going to come off, and they're in the wrong order. Everybody see this? This is the bad order, right? How do we keep this ordering from happening? Exactly, right? Panic, we're in the wrong order. But look at, if these are both on the stack, then we know there's a path from V to U. Remember our loop invariant, was that what's on the stack forms the path. So there is a path from U to V to U. And now we know we see there's an edge from U to V, and hence we have a cycle. And when we find a cycle, what do we report to the world? We say, hey, sorry, buddy, you were supposed to give us a DAG, and this is not a DAG, here's a cycle. And that's it, right? Everybody good? Yeah, so if it's a directed edge, you only go one direction. If it's an undirected edge, when I go this way, maybe I find it. And so then when I come this direction, and then at some point I have to handle it. And when I'm handling it, I come this direction and it'll say, oh, it's found already, right? I'm not saying it's going to be exciting when you go both directions, but you're going to go at most both directions. Something's going to happen, right? When you're here, you follow its edge to here. And when you're here, you're going to follow its edge to here. And something in the algorithm will happen, right? Everybody good with that? That's depth first, breadth first search, total orderings. You want to do Dijkstra's algorithm? Want to do something else? You want to go home? Yeah? No. No, because breadth first search is intrinsically queues, and recursion is intrinsically stacks. That's all I got for you. And, oh, yeah, and one of you came and told me that the last test needed to go one layer at a time, which to me was breadth first search, and you needed to do it with recursion, at which point I said, I have no idea what you guys are talking about. And I meant to ask Jackie about it, and I haven't. But is that why you're asking the question? All right. Did it say, somebody said you had to use recursion.